Let's create our first actual data visualization, a scatter plot. We'll discuss D3 scales, scatter plots, linear interpolation, D3.scaleLinear, selection.call, the first visual stage of dataviz projects. And this is what we're going to build: a 22-line reusable scatterplot component implementation that generates a scatter plot but does not have any axes or labels or margins. This is representative of the first visual phase of a data visualization project, which is when you get the data to actually show up on the screen. Everything so far has really just been a warm-up for this. We've got the data preparation side on one hand, and we've got the marks and channels with the SVG on the other hand, and now is the time that we bring these together. We're going to load the iris data set and then create marks on the screen from that data set using D3 scales. D3 scale is a package that transforms values from data space into screen space. When I say data space, what I mean is values that you might find in a CSV file, like 1.5 or Setosa. When I say screen space, I'm talking about values that you might find as attributes of DOM elements in SVG. For example, X and Y pixel coordinates, radius values, and colors. The goal is to take this data that we've loaded previously, the iris dataset, and merge that together with concepts of marks and channels to instantiate this concept that we know as scatter plot. A scatter plot is a visualization technique that visually encodes data by mapping a quantitative column to X position and another quantitative column to Y position. But when it comes to the code, how do we map quantitative columns to position? To do this, we can use D3 scale. Of all the various types of scales that D3 scale provides, continuous scales map a continuous quantitative input domain to a continuous output range. The domain is data space and the range is screen space. Within continuous scales, we have linear scales, power scales, log scales, identity scales, radial scales, time scales, or sequential color scales. These are all continuous scales. If you think about the transformation that we want to do from these data values to screen space, what does that actually look like for the iris dataset? Well, all four of these columns are quantitative. So any two pairs of these could be mapped to X and Y. Sepal length could be X and sepal width could be Y, for example. X and Y position are typically mapped using linear interpolation. What that means is, of all the sepal length values, we would find the minimum, the smallest value, and also the maximum. By the way, the minimum and maximum taken together is typically called the extent. But anyway, we use the minimum and maximum values, and also we consider some box on the screen that has minimum and maximum X coordinates, and we take all that and derive a function that can take as input one of the values from sepal length and give as output a possible X coordinate value, such that the smallest sepal length value would map onto the smallest X value, and the largest sepal length value would map onto the largest x coordinate value. And the point exactly in the middle between the smallest data value and the largest data value would map to the point exactly in the middle of the largest x coordinate and the smallest x coordinate. This is called linear interpolation because it interpolates the values linearly. The interpolation itself can be implemented with this math right here. And this math is what there's actually an implementation of in d3.scale linear. Linear scales are a good default choice for continuous quantitative data because they preserve proportional differences. So let's do this. Let's use d3.scale linear to create a scatter plot with code. Since we need to load the data first to create a scatter plot, I'm going to start by forking this loading data example from earlier. I'll call it scatterplot simple because the scope of this is just to get some points to show up on the screen and look kind of like a scatter plot. It's not going to include axes and it's not going to have any margins at first. So I'll fork this, open up the code, and just a quick refresher on what the code does. It uses a pre-element, which is pre-formatted and monospace text on the screen, to display state.data using json.stringify. And remember, we're using unidirectional data flow here to load in this CSV file and then store it on state.data, which could be undefined loading or an array of objects, and that gets populated by fetching data.csv, and then when it comes back, we parse the CSV data and then set it to be state.data. All right, so everything here can remain the same. The only thing we really want to change is how the data gets presented. Instead of putting a pre-element on the screen, I'd like to create an SVG instead. And I would like to invoke a component using .call. Selection.call is a function on D3 selections that really just invokes the specified function that you pass in. If you define this function as name like this, for example, see that it gets invoked where the first argument is the selection. And this is the selection that you call .call on. And then whatever arguments you pass in here are also passed into this function. Selection.call is a convenient way to call functions where the first argument is a selection because it facilitates method chaining. Meaning you could say selection.call this, .call that, and then .attr, this and that, and it would all flow nicely. So that's selection.call. In our case, we will create a single SVG and then use .call to invoke a scatterplot. And this scatterplot needs to know somehow about the data. But think about this. If the data hasn't loaded yet, does it make sense to even try to create a scatterplot? No, it doesn't. And I think it would be just a lot cleaner if we only invoke our scatterplot once we're sure that the data has loaded. There are a couple ways we could do this. We could pass an empty array here if the data hasn't loaded yet, in which case no SVGs would get created. Or we could always create the SVG and only invoke the scatterplot if data has been loaded. Either way would work, but I think I'll just go ahead and create the SVG all the time and only invoke it if the data has loaded. To do that, we need to store this selection. I'll call it SVG. And then only if data is not undefined and data is not equal to loading, only then would we want to call the scatter plot on our SVG? Passing an options object that has data defined as, well, we haven't defined the data variable yet. Let me define data as state.data, which we could also do with destructuring like this, which we could also do by destructuring right in here like this. This is a kind of fancy syntax for doing nested destructuring. All right, that's how we invoke a scatterplot function if the data has loaded. Now all we need to do is define this scatterplot function. This function is perfect as a separate module, so I'll plan to import scatterplot from scatterplot.js, and I'm going to create a new file called scatterplot.js, which will export const scatterplot. And I'll define this as a function that takes the first argument to be a selection, and the second argument will be an options object, and that options object will have a property called data, which we could extract to a local variable like this, or like this using destructuring, or by destructuring it straight away. Now all we need to do is render a scatterplot. All right, that's the basic structure that I think makes sense for the code. I made a lot of code changes and haven't run it yet, so let me just make sure that this works. I want to check if scatterplot is getting invoked and that data is being passed in correctly. So I'm going to console.log data just to see if it shows up. Got some errors. Identifier data has already been declared in viz.js. Oh, I see. I destructured it here and up here. Okay, that was just a mistake. Instead of destructuring it there, I'm going to move this destructuring to come before that if. Okay, that should do the trick. And then in the console, check it out. We have an array of 150 elements. And that came from this console.log data right here. Notice that it only printed out after the data loaded. It did not print any undefined or null or loading or anything like that. That means we can write code inside of our scatterplot function that assumes that data is properly defined. All right, we have access to the data in our scatterplot function. Now I just want to make sure that we have access to create marks that have channels on them by doing DOM manipulation on our SVG. To test that, I'll just create a single circle in the middle of our SVG. To do that, we can leverage concepts and code from our mouse follower example. One thing we definitely need to do is set the width and height of our SVG. So over in our scatterplot example, on our SVG, I'm going to set the width and height. And then from the mouse follower, we can grab this code that renders a single circle, which I'm going to drop into our scatterplot component. Selection is the name we're using for our SVG selection. And then we just need to make sure X and Y are defined. I'll just hard code them for now to be, I don't know, 200. And let's see if it shows up. All right, it worked. We have some scroll bars. That problem was solved in the mouse follower with a little bit of CSS. So I'll add that same CSS here. And there we have it. We have created a single dot on the screen. The scatterplot is going to need to know the width and height. So let's make those available. Ideally, the scatterplot would be able to access, in addition to data, the width and height available to it. Then we could take width and use that to compute X as width over 2 to put it right in the center, and also height over 2 as y to put it in the center vertically. This doesn't work quite yet because we haven't passed in width and height from viz.js. In viz.js, when we call our scatter plot, we can pass width and height here in addition to data. But those need to be defined. I think I'll define those up here. Const width equals window.innerWidth, and the same for height. And we might as well use these variables when we set the width and height attributes of our SVG. All right, now the circle appears in the middle because we are passing in width and height to our scatter plot, which we're importing from scatterplot.js. Now we have everything we need to instantiate a visual encoding from a quantitative column from the data to position x and y of these circles. Let's take another look at our output from console.log data. These 4 columns are the options we have for mapping x and y. Let's just say that we want to use sepal length as x. For that, we can define an accessor function called xValue, and that can be defined as a function that takes as input one row and returns that particular value from that row. And similarly, we can define an accessor function for the y value. I'll set that to be petal length. It's these accessor function definitions that define the visual encoding, which columns are mapped to which channels. Because these are arbitrary values, meaning could be defined as different things depending on the data set, the scatterplot component I don't think should really know this level of detail. So I think it makes more sense to pass these in as options from the outside. So instead of defining these right here, I'd like to pass these in as options alongside data, width, and height from viz.js. Right here, when we invoke the scatterplot, we can also include these definitions. And these can just be properties of this object that can be defined just like this. Doing it this way makes it a lot easier later on to change this, or to change this to be custom to a different data set. To make it work with a different data set, all you'd need to do is change these configuration parameters, and ideally you wouldn't have to touch the scatterplot implementation at all. Okay, we have width and height, and our value accessors, and our data. What do we do next? Remember the linear interpolation that we were going to have to do? One of the main ingredients to that is the minimum and maximum values that come out of these value accessors. So let's figure those out. Let's first take a quick look at all the x values by console.logging data.map xValue. This is the same as defining a function right here that accepts as input one row and just turns around and invokes xValue, passing in that row, which can be expressed more simply like this, by just passing in xValue directly to data.map. This outputs an array of 150 elements, but this time they are numbers, not objects. So how do we figure out the minimum and maximum of these values, which taken together is the extent? Well, we can import extent from D3 and invoke that with our data and our xValue accessor. Now we get this array that has the minimum and maximum values for x value, which, remember, we defined here as sepal length. So these are the minimum and maximum values from the iris dataset of sepal length. This extent right here is actually going to be the domain of our x scale. And the range of our x scale will also be an array of minimum and maximum values, but this time these are the minimum and maximum x pixel coordinates, which for the simple version of the scatter plot will go from 0 to width. Now we have everything we need to instantiate an instance of d3.scaleLinear, which we can import from d3, and then after we define the domain and range, we can define x scale to be scale linear, invoked as a function to construct an instance of it. And on that instance, we can set the domain to be x domain, and then set the range to be x range. And because these variables are only used once, I'll just stick these right in here and avoid the extra variables. This creates an instance of scale linear, setting the domain to be the extent of our y value accessor, and setting the range to go from 0 to width. All right, that's how you can use D3 linear scales to create a visual encoding from a quantitative column to x position. Now we can do the same for y. Y scale will be a scale linear instance whose domain is the extent of y value and whose range goes not from 0 to width but 0 to height. But wait a minute, that's not quite right, because remember in SVG the y coordinates are flipped. 0 is at the top, and as the y coordinate increases, it goes from top to bottom. But we want the bottom of the screen to correspond to the lowest value from our y value accessor. So we need to flip these. It's not going to go from 0 to height, but rather height to 0. All right, now we can move on to rendering the circles using these scales. Instead of rendering just one circle, we want to render one circle for each row of data. To do that, we can pass data into the .data method. Now we just need to redefine x and y, such that instead of positioning the circle at the center, these are functions that work on rows of data and leverage the scales we created. D3 scales, in addition to being things that have methods on them, are actually functions that accept values from the domain and return values from the range. Therefore, we can pass into our xScale function a value returned from x value. And we pass in the row that we're working on, D, to x value to get that value out. And we do the same thing for y, just changing x scale to y scale and x value to y value. Now this is what we get. It looks kind of like a scatter plot. Let me just tune down the radius a little bit and we can start to see little dots. All right. Because these variables are just used in one place, I think I'll put this expression right in here and also do the same for y. And it still works. As a quick recap of what our scatterplot function does, it accepts as input selection, which is a selection of a single SVG element, and an options object that's destructured right here that just contains data, the preloaded data array that's always defined as data, width and height, and x value and y value accessor functions. It creates x and y linear scales, setting the domain to be the extent of the value accessor function across the data, and setting the range to go from 0 to width for x and height to 0 for y. And it's inverted for y because 0, 0 is the upper left, and as y increases, it goes down. And we want the minimum value from our extent to correspond to the y pixel coordinate of height, because that's at the bottom of the screen. And then the maximum value from the extent should correspond to 0, because that's at the top. And then we use D3's data join pattern to create one circle for each element of our data array, defining Cx and Cy, the center coordinates of the circles, to be functions that take the row, access the value, and pass the value through the scale, which is a function that takes as input a value from the domain and returns as output a value from the range. So for Cx, that would be a value between 0 and width, and for Cy, that would be a value between height and 0. And we get this beautiful scatter plot. And because x and y value accessors are defined outside of the scatterplot component, we can change them right here pretty easily. So if you want to change this from sepal length to sepal width, all you have to do is change it right here. And the scatterplot updates. All right, so that's how you can create a simple scatterplot using D3. In the early days of a data visualization project that you may be doing, once you get to this point, it's a great milestone. You've loaded in the data and rendered it on the screen. This is what I like to think of as first visual. This scatter plot right here is representative of what you might get as a first visual when you're doing a dataviz project. If you're working with clients, this is a great thing to show them, even though it's not polished, it's not readable, but it shows them that you've got to this point and the project is likely to be a success. To get to this point for your project, you can fork this example and just swap it out to show your data. Keep in mind that x and y need to be quantitative columns for this to work. But there are ways of visually encoding other types of columns, but we'll have to use other types of D3 scales. But we'll get into that soon enough.